Let's recall the definition of relative extrema. If there's an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f. Or you can say that f has a relative maximum at the point C, f of C. If there's an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum of f, or you can say that f has a relative minimum at the point C, f of C. Let's jump to figure 4.2. Just remember that relative max, relative min doesn't have to be the absolute max or absolute minimum. For example, this little hill, that's not the highest point, but relative to an interval, it is the highest point. This valley, that's a relative minimum. It may not be the lowest point, but for a small interval, it is. Let's also remember the definition of a critical number. That's any value of C that makes f prime of C equals 0 or undefined. Theorem 4.2. If f has a relative minimum or a relative maximum when x equals C, then C is called a critical number of f. Some guidelines to finding extrema on a closed interval. Let's look here. To find the extrema of a continuous function f on a closed interval a to b, use these steps. Number 1, find the critical numbers of your function in the open interval a to b. Evaluate the original function at each critical number in that interval. Evaluate your original function at the endpoints of your interval. So that just means you'll calculate f of a, f of b, and f of any critical number inside your interval. The least of these values is the minimum. The greatest is the maximum. Let's look at these two examples. Well, we'll look at two examples, but we're going to look at this one first. Let me get my screen stretched out here. There we go. Find the absolute extrema of the function on the closed interval. We have the function 8x squared over x minus 2, and we're supposed to look at the closed interval from -2 to 1. First thing we do is we take our derivative. Derivative of the top is 16x times the bottom minus the top times the derivative of the bottom, which is 1, over the denominator squared. Distribute 16x, we get 16x squared minus 32x. This term becomes -8x squared. Combining like terms, we have 8x squared minus 32x over x minus 2 quantity squared. This derivative will be 0 when the numerator is 0. In the red ink, 8x squared minus 32x is equal to 0. Let's factor out 8x. 8x is 0 when x is 0. X minus 4 is 0 when x equals 4. However, this critical number 4 is not in the interval given. 0 is, so I put a box around it. The derivative is undefined at x minus 2 equaling 0, and that happens at x equals 2. That's also not in our interval. So we're going to evaluate the original function at -2 and 1, and also at 0. F of -2, sub that into the original function, we get -8. 0 is our critical number that lies within the interval. F of 0 is 0. We expected that too, because if the derivative is 0, you're at either a hilltop or a valley floor. And in the last interval, m.1, substitute 1 into the original function, we get -8. The smallest of these answers are both -8. So we have absolute minima at -2, -8, also at 1, -8. The number you plug in paired with the answer you get is a point on the original graph. The largest answer we got was 0, and that occurred at the critical number 0, so we have an absolute max at 0, 0. Let's jump down to our next function. We're going to take a look at 5 cosine x over the interval 0 to 2 pi. Taking our first derivative, y prime equals negative 5 sine x equals 0. And if you recall from your unit circle, sine x equals 0 at 0, pi, and 2 pi. We have 3 critical numbers. We have to check 0 and 2 pi because those are the interval endpoints, but we also need to check at pi because that's a critical number inside of our interval. Plugging 0 into the original function, 5 cosine of 0 is 5. 5 cosine of pi is negative 5. And substituting in 2 pi, 5 cosine of 2 pi, that's 5. Our largest answer ties at 5, so we have absolute maxima at 0, 5, 2 pi, 5, those 2 points. The smallest answer was negative 5, so we have an absolute minimum at pi, negative 5.